Hi, I am Eric from Intel, and I'm going to show you how Intel is developing new features to bring more security to Kubernetes. I will introduce you to the Trusted Certificate Issuer and how signing certificates for pod-to-pod communication is made more secure. Being secure in Kubernetes or with anything is a challenge. There are many layers of security to consider depending on your threat model. Let's take a look at a typical Kubernetes cluster. You have your master node, which is your control plane. Within that, you have your etcd for storing data. You also have a scheduler and a controller manager. These all interact with the API server. Then you have your worker nodes. There can be many of these. Each one has a kubelet that runs and a kube proxy that makes sure packets of data reach the right destination when you call a service. Within Kubernetes, you can launch pods individually that Kubernetes will schedule on available nodes with free resources, or you can launch a deployment of pods. All of the requests controlling each pod is managed by the API server on the control plane. To securely communicate between pods, you can use signed certificates. You will need to use something like Cert-Manager running on one of your nodes. You could also use the new Kubernetes certificate signing request. If you're using Cert-Manager, you would create a new certificate object, which Cert-Manager would turn into a certificate request. Once approved, Cert-Manager would create a signed certificate and a private key that each pod would use. For Cert-Manager, these are stored in a secret accessible from the pod, but for Kubernetes certificate signing requests, they are stored in a CSR Kubernetes object. Together, the private key and certificate request allow encrypted, trusted communication between pods. One of the nice features of Cert-Manager is that it can support external certificate authorities like Vault, Venafi, Microsoft ADCS, Cloudflare, Let's Encrypt, and many others. These support both public key infrastructure key signing so that your pods exposed to the internet could be trusted by a web browser. That's useful for NGINX pods where you have a public-facing website. It can also support CAs like Amazon AWS Key Management Service, which securely stores your private key in a hardware security module provided by the cloud provider. This is important for securing private communication between pods, kind of like what a service mesh would do. External CAs are great, but what if you want to manage your own private key and not use a cloud service provider? After all, using an external CA adds a lot of unneeded latency. In this case, you could use Cert-Manager as a self-signed certificate authority. It becomes the top-level CA for signing the certificates for communication between pods. Cert-Manager would manage its own private key. When you do this, Kubernetes stores the ca.key in a Kubernetes secret. This is convenient and easy to set up, but it also means that anyone with kubectl access can read the secret and read the private key of the certificate. They can sign their own certificates, and they can snoop in on the encrypted communication between pods. What if there was a way to better secure that private key and not make it so easy for an administrator to see? This is where the Trusted Certificate Service for Kubernetes platform can help. So what is the Trusted Certificate Service for Kubernetes platform? This is a Kubernetes controller that Intel provides that works with Intel Software Guard extensions, also called Intel SGX. Intel SGX is available in many different Xeon CPU SKUs. It allows programs to store sensitive data in encrypted regions of memory called enclaves. As part of this service, there is a trusted certificate issuer that can create private keys that are stored within this encrypted enclave. The really great part, though, is that the private keys aren't visible to anyone, even someone with root access to the machine. It isn't even visible to the issuer itself. When a certificate signing request is made, the trusted certificate issuer executes the certificate signing within that encrypted enclave using the private key stored in the enclave. The signed certificate is then copied back into a secret using standard Kubernetes protocols. Conceptually, you can think of this like a hardware security module or an HSM for your Kubernetes cluster. Best of all, this feature works with any Intel processor that has SGX support. How is it integrated into Kubernetes? As of now with Kubernetes version 1.24, there are multiple ways that certificates can be signed. The Trusted Certificate Issuer works with Kubernetes Certificate Signing Request, which is the built-in way to sign certificates and is the newer way to do this in Kubernetes. It also works with Cert-Manager, which has long been supported in Kubernetes. On our GitHub, we've added guides on how to do this with Istio, which can use either the Kubernetes Certificate Signing Request or Cert-Manager with a trusted certificate issuer to sign certificates for the service mesh. There are packages on our GitHub where you can build and deploy this yourself for extra security, but you can also install it with Helm. In this video, I'll show you how it works on all of them. What is needed to try this out? Obviously, you'll need a Kubernetes cluster setup. Here's mine. I will use this cluster to show you later how a demo of the Trusted Certificate Issuer works. You might have noticed the BMRA logo. That refers to the bare metal reference architecture from Intel. The BMRA is a validated Kubernetes distribution that pre-installs many of the drivers, including for Intel SGX, Intel device plugins, and many other items relevant for Intel hardware. I am using Ubuntu 20.04 LTS as the operating system. Because the issuer uses Intel SGX to create and store the private key, you need at least one node with Intel SGX support. I'm using an Intel 3rd generation Xeon Scalable processor, more specifically an Intel 8380. If I look at the specs of it on arc.intel.com, if I search for the 8380, and then I find the page and I click on it, just scroll to the very bottom, down to the security and reliability section, you'll see that it does support Intel SGX with a minimum enclave page cache of 512 gigabytes. You also need to have the Intel SGX driver installed. If you're using kernel 5.11 or newer, it is already there. If you're using the 5.4 kernel that comes installed with Ubuntu 20.04, the BMRA will install a driver for you, which is what it did for me. It is very convenient. Another thing that you need is the application enclave service manager running. You can also run this as a pod with read-only root access set to true. It needs to access to the var run AESMD socket. This application enclave service manager is responsible for generating SGX quotes for workloads. Finally, you need the Intel SGX plugin running. The SGX plugin exposes to Kubernetes the SGX resources on your system and allows you to configure how many containers per worker node are allowed to use the /dev/SGX enclave and /dev/SGX provision. The default is 20 for both. Those are the prerequisites needed. You can start with your own cluster and add these in following online guides, or you can do this on Microsoft Azure, where the SGX device plugin is already pre-deployed. However, I mentioned I was using the BMRA for my setup. The BMRA is available for you to use as well. If you go to Network Builders on the Intel.com website, click on Technologies, and then go to the Container Experience Kits, there are a lot of helpful guides. If I scroll down to the bare metal reference architecture, and then I click to open it up, you'll see that I get a detailed guide on how to set up an Intel validated Kubernetes cluster that includes support for a lot of different Intel features. The bare metal reference architecture will install everything needed on a fresh install of Ubuntu. There are different pre-configured profiles that can be used that work as templates for pre-installing software. When using the BMRA, you can start from a template with different configuration profiles pre-configured. There are network-specific ones like the on-premises edge configuration profile, access edge config profile, remote central office forwarding profile, or the regional data center configuration profile that are more advanced setups. For more flexible deployments, there's the basic configuration profile with a generic minimum setup. There's also the full configuration profile that is a more complete setup of software and hardware features. There is a storage configuration profile that has support for MinIO. Finally, there is the build your own configuration profile. That's the one I'm using because I only wanted to install some specific features. The config settings I will show you can be done in any of the profiles. The BMRA uses Ansible scripts and some configuration files that allow you to more easily set up many different types of Intel features and includes many popular Kubernetes applications. It supports Intel Speed Select technology for finer grained power management. It includes support for Intel Quick Assist and Intel SGX, as well as installing a Key Management Reference app, or KMRA. Because I had a 5.4 kernel installed, the BMRA configured the Intel SGX driver for me, set up the AESM service, and installed the Intel SGX plugin, and it configured the Intel provisioning certificate caching service for me to be able to do remote attestation. If you're using the BMRA to help with Kubernetes install, you need to set some variables that affect your cluster and some variables for each node. The BMRA guide covers how to generate your group vars and host vars to use as a baseline for different deployment profiles. So I'm going to skip that step and just show you what you need to get this going for the trusted certificate issuer. To set the cluster-wide variables, go into your group vars directory and edit the all.yaml file. You need node feature discovery enabled. So set NFD enabled to true. This will label all your nodes with details of the hardware on each node, including if Intel SGX is supported. Scroll down and enable the SGX device plugin, SGX DP enabled, and set that to true. You can also change the enclave and provision limits if you want or leave the default. Enable the BMRA if you want, but it isn't required. Put in your PCCS API key if you want attestation to verify your enclave is real. This key is unique and available on the API portal. The BMRA can actually set up the trusted certificate issuer for you, but I'm going to skip that step to show you manually. Now let's configure the node for the hardware that it has. Let's look at the inventory.ini file. You'll see I'm using a single node setup. The host vars directory contains YAML files for each node to configure. Edit your node YAML for that node that you want to install to. And now let's scroll down. You'll see that there's a lot of hardware options the BMRA supports. Find the configure SGX setting and set that to true. This will install and configure the SGX driver if you're using a kernel before 5.11, and it will also install the AESM service. Finally, I mentioned above, you don't have to use the BMRA and you can use your own cluster. You just need to make sure the SGX driver is installed and the AESM service is running on at least one Intel SGX capable node. You also need to install the Intel SGX device plugin in Kubernetes, which relies on node feature discovery to label the SGX node. And if you want remote attestation, the PCCS will also need to be running and configured with your API registration key. The BMRA helps make it easier to take care of all of these SGX prerequisites. I should also mention that in addition to the BMRA, we have a virtual machine reference architecture that lets you try out Intel features, but with the convenience of using VMs. You'll need to first check availability of SGX in your VM environment. Let's install the Trusted Certificate service for Kubernetes. There are detailed instructions on the GitHub page that can walk you through a few different install options. You can use Helm charts, which are easy, or can manually install from the source code. On my server, I have all of the prerequisites met, so I will show you how to install the Trusted Certificate service, which acts as a Kubernetes issuer both for the Kubernetes certificate signing request and for Cert-Manager. My setup is a single node cluster on a system that supports Intel SGX, which has already been configured in the BIOS. I already have the SGX plugin installed. I'm going to install this the easy way and use Helm. However, as of now, I need to add the TCS repo to Helm. Once that is done, I can use the command from the GitHub repository to install the TCS. That should create some new custom resource definitions. These are very similar to the issuer type in Cert-Manager, but have some additional parameters for managing certificates signed in the SGX enclave. The TCS issuer works within a single namespace, and the TCS cluster issuer works across all namespaces. You can have multiple issuers, which is like having multiple certificate authorities. The quote attestation is used as part of the attestation processes for validating an SGX enclave. Once everything is up and running and working, you should have a TCS controller running in the TCS issuer namespace. The controller is responsible for managing the signing of certificates and watching for new requests. At this point, you're ready to create a TCS issuer. So first, let's put it in a namespace called Sandbox. We will call this issuer my-ca, use the Sandbox namespace, and use a secret called myCA-cert to store its data. When this TCS issuer is created, the TCS controller will interface with the Intel SGX enclave, which is an encrypted part of DRAM memory, and it will run some code within that enclave to generate a new private key. This private key is stored encrypted in the Intel SGX enclave, and it never leaves it. A self-signed certificate is generated from that private key within the SGX enclave, and it is stored in that myCA-cert secret. Together, the TCS issuer and secret can be thought of as the certificate authority for objects in your Sandbox namespace. Multiple issuers can exist in different namespaces or cluster-wide, and they all work with the TCS controller. This allows multiple certificate authorities to exist. Now, if you look, you'll notice that when the issuer is ready, it should say success. You now have your own local certificate authority in the cluster. If you look at the MyCA cert secret, you will see that there is a TLS.crt populated that is the public certificate of your private key. And let me show you the contents of that secret, but look closely at the TLS.key. You'll notice that it's blank. Normally with a self-signed certificate authority, the private key is visible in the secret, but it's base 64 encoded. Anyone with access to that secret can just read it. With the TCS, the private key is stored in encrypted memory using Intel SGX. It isn't visible to anyone in the cluster, and it isn't even visible to the TCS controller. Although the TCS controller doesn't have direct access to the private key, it can copy in certificate requests into the encrypted memory region, and it can run code within that encrypted region to sign the key. A signed certificate is then returned, and the private key never leaves the enclave. Let's see how the TCS works with Cert-Manager. I am not going to cover how to install Cert-Manager, but let's assume it's running in the Cert-Manager namespace. I will cover the certificate flow through Cert-Manager and how it interacts with the TCS. Start by first creating a certificate, which is a specific type of CRD custom to Cert-Manager. The way Cert-Manager works is you first create a certificate object in Kubernetes and specify which issuer to use to sign it. I'll tell it to use a secret named demo cert TLS to store the signed certificate data, give the certificate a subject of Intel SGX demo, and tell Cert-Manager to use the TCS as the certificate authority. Once you create the certificate object, it'll cause Cert-Manager to go through a certificate signing process. Now we can check that the certificate got created, and we'll see that it isn't ready yet. Cert-Manager is always watching for new certificate objects to get created. When it sees this new object, it will automatically create a certificate request awaiting for approval. And if you look at it, you see it's not approved yet. Now, if we export the details of that certificate request, and I'm going to do it as a YAML, a lot of data is going to scroll by. You'll see things like the creation timestamp, but more importantly, look at the request field. You'll see it's a base 64 encoded request. This is the certificate signing request. Now, just for fun, let's use OpenSSL and look at the subject and decode it. It should match intel.sgx.demo, which it does. This is just the certificate request though. It still needs to go through the certificate signing flow. Now I'm going to approve the certificate request. I'm using the Cert-Manager CMCTL utility to manually approve it. You can also use this utility to deny or renew certificates. Now if you check, it's been approved. The original certificate request or certificate object created now shows as ready. A long, complex process just happened. The request flowed through the TCS controller, and using the private TLS.key in the SGX enclave, the certificate was signed within the enclave. Then the signed certificate was copied into the demo cert TLS secret. So if I look at this demo cert TLS secret, you see I've got a TLS.crt, which is my signed certificate, and I have a TLS.key. That's my private key. Together, I can use those for encrypted communication between pods. Now, just for fun, let's use OpenSSL and look at the subject and issuer of that. And you'll see the subject matches the Intel SGX demo, and it was signed by the SGX self-signed root certificate authority. Now, the signed certificate, it was copied in that demo cert TLS secret. Let's get the original certificate request. And you'll notice that that also gets copied back into the certificate field as certificate. It's the same base 64 encoded certificate field that was in the demo cert TLS. That is your signed certificate. This is how it works with Cert-Manager. However, there is another certificate signing process in Kubernetes that I'm going to show you as well. We can also use the TCS with Kubernetes certificate signing requests. This is the newer alternative way to request and sign certificates in Kubernetes. Outcome is the same, but the process is a little bit different. With Cert-Manager, you create a certificate object first, and it generates a certificate signing request object with the CSR that it creates. Instead, let's use OpenSSL to create the certificate signing request file that has the CSR with a subject of foo and company foo.bar. You'll also want to create the private key at the same time. Both the private key and signed certificate are what's needed for the secure TLS communication between pods. If you look at the screen, you see the private key looks like a standard private key, and the CSR.pem looks like your standard certificate request. Now we can check the newly created csr.pim and confirm the subject and company are foo. The csr.pim also contains the public key. The public key along with the tls.key, which is the private key stored in the Intel SGX enclave, that's what's needed to generate a signed certificate. Now let's create a Kubernetes certificate signing request. We will use the csr.pim created in the above step, but it needs to be base 64 encoded for Kubernetes. We'll need to trim any line feed so that it's a single variable, and we'll call it test-csr. The signer name should be the TCS issuer because that's what will ultimately sign the certificate inside the SGX enclave. Now, if we take a look at the newly created CSR, you'll see that it's pending approval. Let's approve the CSR. Unlike Cert-Manager, this can be done using kubectl, and we'll check that it got approved. So what exactly happened? Approving the CSR kicked off a process where the certificate signing request was taken by the TCS controller, which copied it into the Intel SGX enclave where the private key is stored and initiated a certificate signing within the enclave. The signed certificate was then copied back into the certificate signing request object and into the certificate field. Now let's take a look at that certificate field. Now, when we originally created this, our request was put in there and the request is still there, as you can see. But as it scrolls by, you'll see there's now a certificate field. That is a base 64 encoded signed certificate. If we use OpenSSL, we can decode that and take a look at the subject and company. It should be our foo.bar, and we can see who the issuer was. You'll see it is foo.bar, and the issuer was the Intel SGX self-signed root certificate authority. So this was signed inside of the Intel SGX enclave, which, if I remind you, was that encrypted memory region inside of DRAM memory. You can have multiple CAs that you can use across different namespaces, or you can even use them cluster-wide if you want. And that's how it works with Kubernetes certificate signing requests. It's a little bit different than Cert-Manager, but ultimately you still get a signed certificate. If you want some more information, there is the Intel Trusted Certificate Issuer GitHub repository, which contains all of the source code and instructions for installing the Trusted Certificate service. In addition, there is a link to the bare metal reference architecture user guide, which goes into detail on how to set up the BMRA as a fast path for getting an Intel Kubernetes optimized distribution that can install all of the Intel SGX prerequisites. For information about our notices and disclaimers, scan the QR code.